7.1 Kepler's Laws of Planetary Motion, and worksheet do the first page. This is some really interesting material. I love doing this, as I mentioned, this chapter. If you read through the notes, you can just read through the history of the planetary motion, the study of planetary motion. And they mention Ptolemy, they mention Copernicus, then they mention Tycho Brahe. And you've probably heard of Copernicus before, the first one to say that the sun was the center of the sun, the center of the solar system. Oh boy, stepping on chalk. Before him, Ptolemy is the one that said the Earth would be the center, and he had the Earth-centered model. You don't hear a lot about him, but Copernicus was a big change. It was a neat thing. Tycho Brahe is really an interesting person, but the main thing I think about one of the main things I think is amazing about Brahe, he had a lot of money, a lot of wealth, and he was able to map out. He hired people to make equipment to look at the sky and map out where all the stars, all the moons were every day of the year, and for 20 years of material. He had so much data, but his interpretation was wrong of that data. He had all the data, but he was interpreting it wrong. Kepler was an apprentice to him, and when Tycho Brahe passed away, Kepler inherited all of his data, all of his science material, and he studied over it, and Kepler realized the laws of planetary motion, which began, he wrote the first, or he came up with what's called the first 3 laws of planetary motion, but then Isaac Newton took his work and just went way, and it was amazing what Newton did with that, expanded on it. Okay, so the first thing, here are the laws of motion of Kepler. The first couple don't really have any math in it, then there'll be a little bit of math coming up. The first law says, the orbital path of a planet has the shape of an ellipse. Now, an ellipse is like an oval. So like a circle would be, you know what a circle would be, if we can do that perfect. I can't do a perfect circle there. I'll try. Not horrifying, but not the best circle. That would be a circle. An ellipse is more oval shaped. And it turns out that most every orbit is not a perfect circle. You might think that, but almost all of them are oval to some amounts. Some are more, central or circular than others. Okay, so he said this: the orbit of a moon around a planet, or we can say now the orbit of a planet around the sun. That's what he actually wrote with the sun there. The orbit of a planet around the sun. I guess that's how he said it. I guess I'm saying it wrong. But it's true for a moon around a planet as well. But the orbit of a planet around the sun is the shape of an ellipse. And in an ellipse, there are 2 what they call foci, or focuses. Focuses is not the right word. But the focus would be like here and there. Now, let me show you an example. I might be able to do this with the little... Yeah, I might be able to do it with this little round thing that we talked about that I've shown you before to make my little... Uh-oh, how do I get that thing out of there? Which I've used. Okay, here it is. Okay, so what I'm going to do, I'll try hard to do this. If I took this, it's going to be kind of large. I'll have to fold it. Let's just say that I want to make a circle. You know that if I put my finger here on the chalkboard and I go all the way around like that, all right, you know how you've seen that before. I can make a good circle, a perfect circle going all the way around, right? You can do that with a piece of paper at home. A lot of times if you use a cardboard and you get like a thumbtack or something, you could do that. And I might have already changed my circle already, but anyway, it's something like that. So, you can go all the way around, make it circular. Go all the way around, make a circle. All right, perfect. Okay, let's just say it. Say make a circle that way. Well, to make an ellipse, what you do, and we actually would do this in class sometime too, you take that circle, and what you're going to do is, instead of having a center, one center point, you're going to have one point here and one point there. Now, 2 focuses. I'm saying focuses, but they're 2 foci. A focus, plural of focus, like octopus, octopi. You've heard of all that before. Okay, So now what I'm going to do, oh, I don't even know if I can do it. Can I? Yeah, I have to put I'll put like 2 fingers in here. Oh boy. It might be way too large. I'll try to do 2 fingers far apart like that. So to say my 2 fingers were the foci. Well, now when I make my shape, oh boy. I don't know if you can tell this or not, but what's going to happen is you almost can't tell. But anyway, it's a little bit more elongated because they're really close together. But if I put them farther apart and I did that circle that way, it would be an oval. And there's 2 foci in an orbit. Now, I think you can tell even on the video that that's definitely a little bit longer. I could have done better. Okay, and one of the focus is the sun. So that's what Kepler's first law says. The orbits of a planet around the sun, the shape is an ellipse, and one of the focuses is the foci is the sun. Now, and then here's the Earth. We'll say moving around. Same thing will be true about a moon, the moon going around the Earth, or a moon around another planet. It would also be an ellipse, and the planet or the planet would be at the focus point there. Okay. Now, the period is also T, like we saw earlier. The orbital period is the time it takes to make one circle all the way around. So, the Earth, to go from the Earth, starting here, to go all the way around and come back to the same place again in its orbit, that will be 1 year. The period is 365 days. And yes, we'll have to change that into seconds when we do calculations. Okay. Now, there's actually 2 other terminology words here, aphelion and perihelion. Okay, perihelion is the position the Earth has when it's closest to the sun. But aphelion would be when it would be over here, farther from the sun. Away, and helion is the sun, something like that. That might be where the meaning of that word is. And it says, talks about planets, moons, and comets with periods. Long period comet is one like Hale-Bopp, 2,400 years to make one orbit. Or a short period comet would be like Halley's Comet, which is 76 years. Okay. Now, okay, here's an interesting thing too. In his second law, I could actually use this. I could still use this diagram if I wanted to. I'd like it to be a little bit more oval shape, so I might just kind of change it a little bit. Just so you can it doesn't look nearly as good though, but oh well. Just make it a little bit more oval. Now, here's an interesting thing. I'm going to read what the second law says. During an orbital revolution, an imaginary radius connecting the sun with the planet sweeps out equal areas in equal time intervals. Okay, instead of me trying to draw it, I can take advantage of the fact that we have the camera here, and let me get a pen and I'll do it on the note page, which you also have in front of you. All right, so if you look, I put here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 positions of the Earth around the sun right here, okay? Now, I'm going to just do this. I'm going to connect each Earth to the sun. Oh, wow. Okay, my pen. It might survive. I really need to have a ruler to do this, but I'll just tell you what's supposed to happen. Okay, and my pen's kind of running out. But there it is. I drew the sun, the Earth to the sun all the way around. Now, here's an interesting thing. First of all, you'll notice sometimes the Earth is closer to the sun. Sometimes it's farther away. Think of these as being the 12 months of the year. And you think, wait a minute, really? How can that be? Okay, well, what happens is, think about gravity. When the Earth has the strongest gravity force, it's going to be close to the sun, right? When it's closer to the sun, there's a stronger gravity. When it's far away, there's a slower gravity. So the Earth, when it's closer to the sun, it moves really fast. So the Earth going around, we'll just say it goes really fast around that curve. Then it goes slow here. Then fast around it and slow there. All right, fast and slow. Okay, so that's strange. Okay, Now, anyway, the point is this. Even though the Earth's speed is not constant, it's what Kepler's second law says is that it sweeps out equal areas in equal amounts of time. So what that means is, if I go from one Earth to the other Earth position here, that would be like 1 month, 2 months, 3 months, 4 months, 5 months, and so forth. The area, that would be the same amount of time. Think about that. To go from one point to another would be a month. Just say each one of those is a month away. But then look at that month. You go jump to there, then jump to there. Now, I'll talk about what month that of the year that is in a moment. But first, here's a point to know. If this were a giant pie, an elliptical piece of pie, apple pie, and you cut it up into the pieces like that, according to Kepler, if I did my lines right, everybody will have an equal piece of the pie. Even though that looks like a really big piece, I didn't draw it so good on my diagram, but this one would also be an equal piece from these two to the sun and back. It's a much longer piece. So the area is the same as that one. I didn't draw it very good at all on mine, but it should be. I intersected the lines. But if I did a line straight from there to the sun, and from that one to the sun, that pie piece is equal to that pie piece. So equal areas are swept out in equal amounts of time. Now, about where is the Earth? Well, that's another interesting thing. When is the Earth closest to the sun? I don't know if you knew that or not. It'll be closest to the sun in what month of the year? What time of the year? In the summer, in the winter, spring, or fall? What do you think? And it will be at the, can you believe it? The winter. In the winter, it is the closest. So the perihelion, that would be the winter. Like maybe like December, okay? And then, so it goes really quick around this part, moving really fast. It's close to the sun. But then the farthest from the sun is the summer. Oh, and you know what? I better qualify that. It will be the winter in the northern hemisphere. In the north hemisphere, where we live. But not for people that live in the southern hemisphere. If people live in Brazil or in Australia, that is going to be their summer, and that's going to be their winter. But we'll talk about ours first here. All right, so summer is when you're farthest away. Now, see, what happens is, why is it hot in the summer, though? It's because the Earth, the axis of the Earth, is not, it's not perfectly lined up. Like the axis of the Earth is like the equator. Let's say the equator. The equator is not lined up just like that with the sun. If it were, then it means that the Earth, as it moves around, would all get equal amounts of light. You see right here, the north and the southern hemisphere would, but they don't. What it really does is this, and you've probably heard of this, the Earth is tilted on its axis. So because of that, in the winter, where we live in the north, this is really exaggerated. Let's do that. In the winter, look at what happens. Almost all the sunshine hits the southern hemisphere, and not any in the northern hemisphere. It does not. That would be the axis. Here's the North Pole and the South Pole. So not much sunlight hits the north as much. In fact, you know that Alaska and those areas, it'll be like dark. It'll be dark all night long. All day long and all night long in that time of the year. And there'll be sunshine in the summer. In the summer, like in Alaska, they won't even have any darkness at all. And so, we can really exaggerate it. Well, it's about the same I did there. So let's put the north here and the south here. Notice now in the summertime, even though we're farther away, we're getting a lot of sunlight on the northern hemisphere as it moves around. But the southern hemisphere doesn't. We have our summer, they have their winter at that time. So anyway, I thought that would be an interesting thing. You'd like to see how that worked out. Okay. Now, and this is what I just told you right here. Kepler recognized that for his second law to be true, the planet would move faster when it's closer to the sun and slower when it's farther from the sun. But the planets would sweep out equal areas of the ellipse in equal time frames. So as I showed you, every little Earth would be like 1 month apart. Okay, the third law. Now this is where the calculations come involved, and I'll have to show you more of these in the class as well. But what I'm going to do, I'll give you his equation. And this was amazing because to figure this out was something. This helped out Newton and everyone else and showed them, oh wow, there's math, there's an order to this universe with all these stars and suns and things we see above. going on. And here it is, kind of a weird equation that we won't use we'll use it a lot here, but yeah, later on we'll use some other ones in its place. But it says this, as you can kind of tell. The period, let's just say that you have you have to have two moons or two planets going around a common central body. So let me read what I wrote here in the notes. There's a math relationship between the period of a planet's orbit and the distance from the sun. Okay. Oh, I'm so sorry. I wrote T and T as in period, and radius, and radius. Now this is called the R is the orbital radius. And what that means is like imagine it were a circle. How far are you from the center? Now, in fact, we will treat a lot of these as if they are a circle. Even though they're ellipse, we're going to treat them just like as they're a circle. Let's call that the central body, the C right there. Okay, so it says the square of the ratio of the periods of any two planets involving the sun is equal to the cube of the ratio of their average distances. Now, so here's the way we're going to have to work this out. This is going to be like the sun, the central body, and it can be the sun in this case. All right, we'll just put sun, center, C. Then you're going to have two different planets going around it. Let's just say you have the Earth here, you have and maybe Jupiter here or something like that, or Saturn or what. I should know my planet, shouldn't I? Okay, Mars is next, right? So let's put Mars there. Okay, so Earth and Mars. Now, what they're saying is, if I take the orbital radius of the Earth, we're going to say that will be from the Earth to the center of the sun. And, all right, that will be the orbital radius of the Earth. Call that radius A. And let's get from Mars to the center will be radius B. Well, I know that the period of time it takes to go around will be period A for the Earth. And then the period for the Mars will be period B. The reason why this is so amazing is because the scientists could see moons around planets, and then later on they figured out where planets were around sun, and they were able to figure this out, how long it takes to go around one. If we know that the Earth takes 1 year to go around, and you can look at another planet, and you know how long it takes for it to go around, you can find out how far it is from the sun. And so there's a lot of neat stuff that you can calculate from that. All right, so I'll do the first example here. Galileo measured the orbital sizes of Jupiter's moons using the diameter of Jupiter as a unit of measure. Sorry. Here's what he did, and this is a neat thing. He looked at the telescope. Let's say he's looking through his telescope. Galileo invented the telescope as well. And let's just say he took a piece of glass. Like we could take, if you've seen like in classes, a transparency film. A teacher, like they write on a plastic film. Let's say he looks at a piece of glass. Now, he says, okay, here is, we'll just say there's Mars. And here's one moon of Mars, and here's another moon of Mars. Okay, so what he could do was this. It's kind of an interesting thing. Let me make Mars bigger. Or let's say Jupiter in this problem, so we'll let it be Jupiter. Let that be Jupiter, and these are two of the moons of Jupiter. So what he did was, on his glass, he could really color in that image on the glass. Then he could color in, like let's just say this one. Uh-oh, I overdid it. He colors those both in. Then he takes it off, and he measures it and says, okay, now, I've got my glass pane. I'm moving away from the telescope. I'm going to measure how long this is, the diameter of Jupiter, according to my little, on my view, and the diameter of the moon it has going around it, right here. Okay, then he says, okay, how big is the moon, or how big is Jupiter? So what he did was he said, oh, I'm sorry, he didn't measure, well, he could measure the diameter of the moon, he didn't. He measured this diameter, and he called that 1 unit. Then he said, how far, okay, now I'm going to use that unit, how far away is this moon right here? And he said, well, it's about 1, 2. We'll just say it's about 2 units away. It's about 2 Jupiter radiuses away. Okay, and I'll put one up here. How far is that one? Well, it might be like 1, 2, 3, 4. That one might be 5 units away from Jupiter. So they're using Jupiter to measure how far away the moon is. Isn't that weird? Isn't that neat? What a neat idea that Galileo had to do that. Even though he can't go out there and measure it, he can make a mark on his paper, on his plastic glass film, and then keep doing it over and over and measure it. And he would do this many times for years and years and years. And the more you did it, the better your math got. Okay, the closer you got to being the right thing. And he was able to calculate it. All right, so here's what he found. Io has a period of 1.8 days. So for Io, the period of, in fact, I like to make the equation that way. The period of Io is 1.8 days. And he also took the period of Callisto. We'll put UC. Callisto has a period of 16.7 days. Now, the radius, he said the radius, it will equal the radius of Io over the radius of Callisto cubed. These two squared equal that cube. So let's plug in our numbers. For Io, it's 1.8 days. Now, let me explain something also. I told you about period has to be in seconds. Well, if both of them are in this equation, if they're both in the same unit, it's okay to leave it in days. But if they're not, you'll have to put them in the seconds in another problem later. Okay, then it says, okay, Io has the closest moon to Jupiter has a period of 1.8 days and a mean distance of 4.2 units from the center of Jupiter. So Io is 4.2 units for its radius from the center of Jupiter. So what will be the radius of Callisto?